thank you so much again, Professor Schnetzer, for joining us today. For today's professional speaker series, we have the luxury of being able to hear from someone who is working with high school students in particular for cosmic ray detection, and really looking at muons in particular. And, how is it that we know that these muons are actually coming to the surface of the Earth? So hopefully we'll be able to hear a little bit, and we'll be able to make some of those connections that you guys are doing in terms of your own experiments as well. So Professor Schnetzer, please feel free.
Okay, well, my name is Steve Stetzer. I'm a professor at Rutgers University in physics, and I've been at Rutgers for 39 years. Most of that time I've been doing high energy physics, and for the past 25 years I've been working on the compact muon solenoid experiment at the Large Hadron Collider at CERN. You've probably all heard about that. So, and then in my spare time in the summer, I run a outreach program for high school students, in which, among other things, we allow the students to use cosmic ray detectors to measure muons produced by cosmic rays.
Okay, so some of the things that the students have been working on so far is that they've actually been working with a light sensor. So they've been looking at potentially being able to collect some amount of ambient light in everywhere from the UV wavelength all the way through the infrared wavelength. And one of the things that they're looking to do is potentially think outside the box of just looking at visible light as well, right? So, how is it that they can detect something in a similar way that a light sensor might be able to detect light? So I know for you guys, when you guys make the detection of cosmic rays with these muon particles, what exactly is it that's happening there? What's going on?
Okay, well, for one thing, with these cosmic ray muons, they're charged particles. A muon is like an electron. It's a heavy cousin of an electron. It's just like an electron, except that it has a mass which is about 200 times greater. And like the electron, it carries an electric charge. So when it goes through material, it can excite the atoms in the material. And then when the atoms de-excite, they emit photons, mostly in the ultraviolet. Okay. And so a cosmic ray muon, a charged particle going through a piece of, say, plastic, will produce a large number of ultraviolet photons, which we can then detect. Mm-hmm. So in this case, unlike what your students may be doing, we're detecting single particles. A single muon going through, say, a 1 centimeter piece of plastic produces enough light that we're able to detect that single particle. But when you're detecting, visible light or UV light with your light sensors, in principle, it's possible to detect a single, visible photon, but you have to get your detector really, really cold so the thermal noise is reduced enough. So you're detecting a flux of photons, not single photons. But we're here with these charged particle muons, we're detecting single muons.
Okay, wow, that's incredible. So how do you know that you've actually detected a single muon, right? So for our students, right, with their light sensors, just like you said, right, they're not necessarily detecting a singular photon, right? They're detecting lots and lots of photons simultaneously being bombarded. So if that's the case, how do you know that you've actually seen, quote unquote, one particular, I guess in your case, muon?
Okay. Well, can I show some of my slides that might help?
Please, yeah, feel free, absolutely.
So I had an introduction here on cosmic rays, but I'll skip over that and go to the detection.
Definitely want to come back to some of that as well, but.
Okay. So here is our equipment. You can see here for detecting these cosmic ray muons, and this is the equipment that we give the students, the high school students that work in the QuirkNet program in the summertime. So the equipment consists of these pieces, which are plastic scintillator. It's scintillator about 1 centimeter thick. It's wrapped in black plastic tape to keep it light shielded. And then on the corner of each, there are 4 pieces of plastic. On the corner of each piece, there's a photomultiplier tube. And then coming out of the detector on these cables that you can kind of see here are signals, which then go into this logic board, which can do coincidences and things with the signals coming from the various detectors. So as I said, when one of these muons goes through this piece of plastic, it deposits about 2 MeV of energy. Now, you might not know what that means, but the energy of a visible photon is about 10 electron volts. So this is like 100,000 times more energy deposited than the energy of a single visible photon.
Wow.
And so that means that we can detect these single muons with essentially 100% efficiency. And so we use pieces of scintillating plastic. And I don't know if you can see my camera very well, but here's one piece. It's a special type of plastic. And so when the muon, this red track you see over here, goes through the plastic, as I said, it excites the atoms. And when they de-excite, they emit ultraviolet photons, which kind of bounce around inside of the scintillator. And one muon traversing 1 centimeter of this plastic will emit about 100,000 ultraviolet photons.
Wow.
And then, as I said, these photons bounce around, not all of them, but if you know about the critical angle, if the angle of incidence between the photon and the surface here is greater than what's called the critical angle, then it's perfectly reflected.
So we have some reflection and refraction going on here then as well.
Right.
Gotcha.
The photons that hit with an incident angle greater than the critical angle are completely trapped. They just perfectly reflect, and they keep doing that. If the angle is less than the critical angle, then, as you said, they refract and the light comes out. But
well, I was just going to say, just to clarify for the students, so this is kind of a similar thing as to how fiber optics might work as well, right?
It's exactly the same principle.
Okay, gotcha. Yeah. All right, go ahead, continue. Sorry.
Okay, so not all the light gets trapped by this total internal reflection, only the light that's hitting this surface at an angle greater than the critical angle, but that's maybe about 10% or so of the light. And then it just bounces around until it either hits a side or an end. Then when it hits, say, the end, it's hitting at a complementary angle to the angle that it's hitting the upper and lower surfaces. And so then it will escape, like this red one here. And so if we put a photomultiplier tube on the end, those photons that escape will go into the photomultiplier tube. And if it's designed very well, you can collect about 1% of those 100,000 photons. So you get about 1,000 photons. Okay. Now in these detectors, you can see the scintillating plastic wrapped in black. And here at one corner is the photomultiplier tube. So it's not covering a whole end, it's just a corner. And so with these detectors, we only collect about 0.1% of the photons. So we might get, on the order of 100 photons into our photomultiplier tube.
Okay. So okay. I just want to make sure that I have it clear. 100 photons, I feel like, would be not a lot of, I guess, light by how myself and the students might think of it. So how do you get something to be so sensitive that it can see just 100 photons then? Right. Or are you doing something a little bit different?
No, that is the role of the photomultiplier tube.
Oh, so I see. Okay.
We have this plastic, and in the end, roughly for one muon going through this plastic, about 100 photons will come into the photomultiplier tube here on the end.
Oh, okay. So then how does the photomultiplier take the 100 photons and make it something that is it making it something visible or?
No. So what's happening? Well, first of all, let me show you a photomultiplier tube.
Sure.
So here's the photomultiplier tube that's attached to that piece of plastic I was just showing you. Okay. And here on this front surface is what's called a photocathode. We'll talk about that in a moment. I have another photomultiplier tube that wasn't working, and so it's been taken apart. And so you can see the inside of this photomultiplier tube. Okay. Now, let me describe how those function. So here's a schematic. So you see this little squiggly line here, that's a photon. So one of those 100 photons comes in, and this red piece is what's called a photocathode. It's a very thin piece of material, and it's made out of a material that has a very low work function. That means it's very easy to knock an electron out of the material.
Gotcha.
The electrons aren't trapped too strongly in the material. So this UV photon coming in can knock out an electron. The efficiency of that is about 20%. So only about 1 in 5 photons will knock an electron out. Okay. And so we had 100 photons coming in, 1 in 5, maybe we'll end up with about 20 electrons coming off of this photocathode. Okay, that's so 20 electrons, as you said, is a very small number of electrons.
Mhm.
But this photomultiplier tube multiplies by a huge amount the number of electrons.
Oh.
And so the way this works, inside the photomultiplier, there are a series of what are called diodes. These curved pieces here, curved pieces of metal. And there's about 100-volt difference between each neighboring diode. So the difference between this diode and this diode is about 100 volts. And the difference between this diode and this diode is another 100 volts. And then it just cascades down. Okay. So one of these photoelectrons coming out of the photocathode will hit one of the diodes, and it's being accelerated toward the diode because there's a voltage there, an electric field, and that's accelerating this electron. So it hits this diode with a reasonably high energy. Mm-hmm. And that will knock several electrons out of this diode. Okay. So let's say it's 3. Now we have 3 electrons hitting this diode. Each one of those will, on average, knock out 3 electrons from this diode. And so now we'll have 9 electrons going up. And then each one of those 9 electrons will knock out 3. Mm-hmm. So we'll have, 27 here. 7, yeah. And you can see it multiplies. Now you can do the math. Well, I haven't done the math here yet. Let's go to here. Still not. Okay, so this is just showing things that I've been discussing. The photocathode. Sure, yeah. Here are the diodes. And now, okay, so let's say that we have 12 diodes. That's typical for a photomultiplier tube. And let's say that at each diode, mm-hmm. An electron hitting the diode knocks out 3 other electrons. Okay, then we end up with the number of electrons coming out of the end, this very last diode, the number of electrons coming out of that very last diode is going to be 3 to the 12th. Right. And 3 to the 12th is approximately 500,000 electrons. Wow. Okay. Now that's something you can do something with and make a rather easily detectable signal.
Sure, absolutely. Okay, I see. That makes sense to me now. Gotcha.
Okay. Should I go on a little bit more? Please. Okay. So, and these 500,000 electrons, they come out in a very short period of time. They come out in about 1 billionth or a few billionths of a second. So we have a very narrow pulse, only a few billionths of a second long. And within that pulse, there's about 500,000 electrons. Mm-hmm. So that means there's a current, and then that current goes through a resistor and makes a voltage. So here's the calculation. So remember, I said typically there's about 100,000 or 10 to the 5th UV photons produced in the scintillator. Mm-hmm. And then we collect about 0.1%, 10 to the minus 3 of those. If we worked harder, we could collect 1%, but we don't need to. Mm-hmm. And then there's a 20% efficiency for a photon hitting the photocathode to knock out an electron. And then there's this multiplication factor from the photomultiplier tube that we just discussed of 500,000. Okay. So the number of photoelectrons will be the 100,000 UV photons times an efficiency of 10 to the minus 3 to collect them times the photoelectron efficiency, which is 20%. So we end up with 20 on average for a single muon crossing the scintillator. We end up with 20 photoelectrons coming out of the photocathode. Okay, so here's that 20. And now we amplify that by 5 times 10 to the 5th. Mm-hmm. And now I'm sure all your students know that the amount of charge in a single electron is 1.6 times 10 to the minus 19 coulombs. I've just rounded up to 2 times 10 to the minus 19 coulombs. And then those electrons come out in a time of a billionth of a second, 10 to the minus 9 seconds. Mm-hmm. So that gives a current of 2 milliamps, 2 times 10 to the minus 3 amps. Yeah, not a huge current, but not bad. And now if you take this current and run it through 50 ohms, usually you have a 50 ohm cable, right? So you're running it through 50 ohms, then 50 ohms times 2 milliamps gives a signal of 0.1 volt, 100 millivolts. Okay. And then this is a little, well, sorry, let me write. This is a little pulse that looks like this, mm-hmm. where I'm plotting this as a function of time. Yeah. And this is about 10 to the minus 19 minus 9 seconds, 1 nanosecond, a billionth of a second. And this height is about 0.1 volt. Okay. So that's something you can measure You can run it through a logic circuit and make digital signals out of it, and then you can do logic coincidences and so forth with those signals.
Okay. So I don't want to dig too far into the rest of the presentation that you're going to give, but are you going to talk a little bit about what coincidences are?
Okay.
Well,
yeah.
Okay.
That comes next.
Okay.
Well, okay, but first I have to say something about noise.
Please.
Because there is noise. So in addition to a signal from the muons traversing the scintillator, what we just calculated, it'll give a signal of about 100 millivolts, 0.1 volt, a pulse of about a nanosecond, 10 to the minus 9 seconds. There'll be spurious noise signals. And I meant to not show you this, but ask you, but because I thought the students would be there, but it doesn't matter since they're not. So there's going to be noise. Why is there noise? Well, if we go back to this photocathode, way back here, as we see when a photon from the scintillator hits the photocathode, it knocks out an electron. But there's going to be thermal noise. There are going to be molecules hitting the photocathode that are at the room temperature.
Right.
And once in a while, those will knock out an electron. So that's thermal noise. If you wanted to get the noise down, you'd have to make your photo multiplier very, very cold. But at room temperature, it's going to be fairly noisy. And then the photoelectrons that get knocked out of the photocathode due to this thermal noise, well, they go through the chain of the photomultiplier tube, so they get multiplied by this factor of 500,000 also. So they'll produce a reasonable amount of signal, a sizable signal. So what do we do? And typically that noise rate is comparable to the rate of cosmic ray muons going through the scintillator. But we need to get rid of it.
Right.
How do you get rid of it? Well, it's easy to do. We make a coincidence. You take two of these detectors. If you can see this, and you stack one on top of the other, right? And so now, if the cosmic ray muon from the sky comes through, it's not going to, in general, stop. Once in a while, and very, very rarely, a muon will stop in the scintillator, but most of the time, it'll just go through, and so it's going to hit both scintillators. So then, in a time window of a few billionths of a second, say 10 billionths of a second, we'll get a signal out of this photomultiplier tube, and within that same time window of about 10 billionths of a second, we'll get a signal out of the other photomultiplier tube.
I see.
If those two are in coincidence, then it tells us it was really a muon that went through. Okay. Because the probability, the rate of noise signals coming out of the photomultiplier tube is comparable to the rate of signals due to the muon. But these noise signals just come at random times, right? The probability that we'll get two noise signals that come, one from this photomultiplier tube and one from this photomultiplier tube in this 10 nanosecond, 10 billionth of a second window is vanishingly small. So just by putting two counters in coincidence, we can essentially completely get rid of the noise and just have and be sure that if we see a signal in both photomultiplier tubes and both scintillators, that was definitely a charged particle going through them.
Oh, I see. So I have a question then, right? So some of our students are also looking at this idea of, efficacy in terms of how true their data is. So if they were trying to really, right, so say a group was working towards really minimizing those uncertainties, specifically with the instrument, based on what you're saying, would it also then potentially make sense? Is it possible even to, instead of just looking at two photomultiplier tubes or two scintillators, would it could you stack 3 or 4 of them together as well? And then be able to make the statement that if a muon goes through the 3 of them or the 4 of them, right, that you would be able to get a better understanding of, is it really a muon?
Yeah.
Wow.
Yeah, we could stack more, 3 or even 4, as you said. But even just 2, you have essentially complete confidence that it really was a charged particle that went through 2. But if you wanted more confidence, 99.9% rather than 99%, put another scintillator there. But you're referring to the light that the students are detecting. You see, they can't do this coincidence measurement because when you're detecting light, visible or ultraviolet photons, your detector is absorbing them.
Right, right.
So they don't go through and hit another detector. Whereas here, our scintillator doesn't absorb the muon. It just passes through,
Right.
releasing some energy, but just passing through.
Okay. So I actually want to take a moment to give you a chance now. I think this would be a good time to go back to the beginning part of your presentation that you had as well. So what exactly are muons then as well, right? Like what are we really talking about here in case some of us don't really understand what we mean when we say an elementary particle, if you will?
Mm-hmm. Okay. So as I mentioned earlier, a muon is you can really think of it as a heavy cousin of an electron. It's exactly like an electron in terms of charge and spin. And like an electron, it's a fundamental particle, but it's 200 times more massive.
Okay.
And so muons don't naturally exist here on the Earth. The only way they occur is either because a very high energy cosmic ray hit the atmosphere and muons come from that shower. I'll talk about that in a moment. Or we can produce muons in a high energy accelerator that we build.
Okay.
But other than those two ways, muons, because they're so massive, they don't exist naturally on the Earth.
I see.
Okay, so let me talk a little bit about cosmic rays, which is the source of where these muons are coming from. So as I think everyone knows, the Earth is continually being bombarded by particles from outer space, and they're mostly very high energy protons, nuclei of hydrogen atoms. And most of them come from the explosion of stars called supernova. What happens to a star when it reaches the end of its life cycle? If it's massive enough, it'll turn into a supernova. Mm-hmm. And there's a supernova within our Milky Way galaxy about once every 100 years or so. And that's where these high energy protons, these cosmic rays are produced. Now, the very, very highest energy cosmic rays are too high of an energy to be produced by supernova. So they're definitely coming from outside of our galaxy, some very energetic source outside of our galaxy. And it's not very well known yet exactly what the source of those are. There's some guesses, but it hasn't been established what the source of the very highest energy cosmic rays that are coming from outside the galaxy is. So that's an active area of research.
Okay.
So here's what they sort of look like. So these tracks you see coming in, these are the high energy protons, and they travel through a long distance of space, interstellar space, hundreds of thousands of light years. Mm-hmm. But then when they come and hit the Earth, some of them will hit the Earth, as soon as they hit the atmosphere, then they interact with the nuclei in the atmosphere.
Huh.
Because these are protons, they have quarks, they interact strongly with the nuclei that also contain quarks. And that interaction, because these are very high energy protons coming in, it produces a shower of an incredibly large number of particles. Oh. The number of particles is proportional to the energy, but there can be, for the highest energy cosmic rays, there can be millions of particles produced in these showers.
I see.
But they only start in the upper atmosphere when the high energy proton first reaches the atmosphere, about 10 kilometers up. That's where these showers take place.
And I assume that interaction between that proton as it's going through the atmosphere, right? That must be some kind of quantum-based effect then, I'm assuming?
Well, it's due to what's called the strong interaction, or sometimes called quantum chromodynamics. Okay. It's a strong interaction between quarks. The proton coming in, that contains quarks, two up quarks and a down quark. And then the protons and neutrons inside the nitrogen nuclei that are in the atmosphere, they contain quarks. And so there's this very strong interaction between the quarks and the proton and the quarks and the nuclei.
So it's almost kind of like what we're seeing in the quote unquote shower is almost like that bombardment ripping of, okay, I see. Gotcha.
Yeah. Yeah. So
what are all of these different what are all these different denotations that we're seeing here on the image?
Okay. So here's another image of a shower. Here's the primary cosmic ray, a proton coming in. And at this point, it interacted with, say, a nitrogen nucleus, and then it produced many, many particles. These green tracks that you see, those are pions. Okay. Most of the particles that get produced are pions, and I'll talk about them in just a moment. But these pions that are produced, they also contain quarks, and also they don't live very long. They live for about 20 billionths of a second.
Okay.
And so when a pion, well, let me go to the next slide. When a pion decays, it decays to a muon and a neutrino. Yeah. So here's a pion. It's a schematic of a pion. It can, for example, there are three types of pion, but a pi plus pion consists of an up quark and an anti-down quark.
Okay.
If it were a pi minus, then it would consist of a down quark and an anti-up quark. That would give it a minus charge. And then there are also neutral pions, pi zeros, and they consist of, let's say, a quark and an anti-quark.
Okay.
A bar over the symbol means anti. And these quarks here could either be, it's actually a mixture of up, anti-up, plus down, anti-down. But in any case, a pion is a bound state of a quark and an anti-quark.
Okay.
Like for example, this.
Bound state referring to the fact that they are together. That
Yeah, they strongly,
okay.
They strongly interact with each other, and so they're very strongly bound to make this pion.
Okay.
Now, as I said, the pion only lives for about 20 billionths of a second. And when it decays to a muon that we've been talking about, and also a muon neutrino.
Okay.
So if we go back to this picture, you can see here, this pion decayed. This dashed line is a neutrino, and the solid line is a muon. Okay. And here, this pion decayed to a neutrino and a muon. This pion decayed to a neutrino and a muon.
I see.
So up here at around 10 kilometers up, about 30,000 feet high, there's a lot of particles up here, all these pions. So if you fly take a flight, a transoceanic flight, most of that flight is up around 30,000 feet, which is where the shower is. So you get a fairly hefty dose of radiation from the shower, from the particles up here. But then when we come down to the surface of the Earth, the only remaining particles, all these green tracks of pions have all decayed away. There are no pions hitting the surface of the Earth. The only thing hitting the surface of the Earth are muons, because they live long enough to reach the surface of the Earth, and neutrinos.
Okay.
Now, neutrinos you can't detect because they're so weakly interacting. They're not electrically charged, and they just pass right through the Earth without interacting. So we can't detect the neutrinos unless we build a really huge detector. But these muons, they're charged particles, and it's very easy to detect them by the means we were just talking about a moment ago.
Okay, I see.
And then just to give you an idea of the rates, let's see, where did I talk about that? Maybe I talked about that back here. No, it's coming. Okay. Okay. Yeah. So the particles hitting the surface of the Earth are certainly not the primary cosmic rays, the high energy protons that hit the upper atmosphere. The particles hitting the surface of the Earth are the muons, which these solid red tracks you see in the picture here, which are the remnants of the shower.
Okay.
And the rate is such that a good rule of thumb is that if you hold out your hand, there's approximately 1 cosmic ray muon per second going through your hand.
Oh, interesting. Okay.
Or also about 1 cosmic ray muon per second going through your brain, through your head. And so it's interesting. This is actually an irreducible source of natural radioactivity. You can't get rid of these muons from the cosmic rays unless you go about 100 meters underground. Okay, then you can get away from them. But on the surface of the Earth, you're subjected to this radiation, which is about 30 millirem per year. And the typical dose that people on average get per year from radiation, uranium and thorium in the soil and so forth, is about 300 millirem. So about 1/10 of your radiation dose per year is coming from these cosmic rays. And if you live in Denver, higher up, the more muons there'll be. And so if you live in Denver, it's about twice as high.
Wow. Okay. Interesting.
So yeah, and so that's Then from here we've already have gone through all these slides. And then from here I talk about how to detect those muons.
So I actually do have a question about this image. So, like I shared with you a little bit earlier, our students, the reason why they are looking at these sensors in the first place, right, and looking at potentially other kinds of sensors that might detect things that are similar in different ways.
Mhm.
Here we have a particle like a muon rather than, a whole bunch of those particles all at once.
Right.
I do see here some high altitude balloons as well as,
Mhm.
it's showing us kind of where a plane would be. So I do have
Mhm.
a question. If we didn't have an atmosphere, right? So let's say, for example, that
Oh.
that was somehow
Mhm.
possible, right?
Mhm.
Would we be able to actually detect then some of those primary cosmic rays as well?
Well, yes. If there was no atmosphere,
Uh-huh.
then these primary cosmic rays coming in,
Right.
these high energy protons, they wouldn't interact.
Interact. Yeah.
They would come all the way to the ground. Right.
Okay. So then I guess my next question is one of the things you mentioned is that the pion doesn't exist for long enough, right? Inside
Right.
once it kind of after it goes to that initial kind of bombardment. How long is
Mhm.
it that the muon actually does exist for?
Well, the muon lives for about 2 millionths of a second, two microseconds. So that's about 100 times longer than
Uh-huh.
a pion.
Oh, wow.
And
Okay.
so a muon will decay after about 2 microseconds.
Uh-huh.
And when it decays, here's a muon decaying, it decays to an electron and two neutrinos, a neutrino and an antineutrino.
Okay.
And that the average lifetime for that is about 2 millionths of a second, which
Okay.
is short, but it's 100 times longer than the lifetime of the pions. So that's why the muons can reach the surface of the Earth. They live long enough to reach the surface of the Earth, whereas pions do not.
Okay. Wow. Awesome. So many of our students, right, the context for these sensors as well is that they're looking to eventually be able to launch different sensors, right, collect data either in suborbital space or orbital space as well, right? So we're talking, right, outside the bounds of 100 kilometers all the way up to about maybe 250 kilometers as well. So high altitude balloon launches, we know, can go anywhere between kind of like right inside that 10-kilometer to 50-kilometer zone, and ones that are good, even higher than that.
Mhm.
Um, what does cosmic ray detection then potentially look like in space? Would you be able to provide any kind of insight for us into what that might be?
Well, um,
So I know you talked about the scintillators here on Earth, but potentially could the students make quote unquote a miniaturized version almost, right? And be able to make detections of pions if they were to get, a device that can make those measurements into that 10-kilometer, 15-kilometer zone.
yeah, yeah. Okay, so you could take a detector similar to the one we've been talking about, just these simple scintillation detectors,
Uh-huh.
and if you put that on a balloon, say, went up to, a few thousand, a few thousand kilometers, then you'd be in this shower of many particles, and
Right.
so the pions going through the plastic would produce essentially the same amount of light as a muon going through,
Okay.
but you'd have many, many, many more pions,
Right.
up here at
Sure.
10,000 kilometers than muons at the surface of the Earth. So you'd have a really high rate of particles going through your detector.
Do you have any idea, like, is that something that's been done before? Have maybe other groups or other scientists, either at the collegiate or, independent research facilities, have they looked at something like that? Are you aware of anything?
Well, yeah, I'd say back in the 30s and 40s, people
Mhm.
sent up balloons to look and measure cosmic rays.
Okay.
In fact, I have here in my slide an interesting story of the discovery of cosmic rays. That was by Victor von Hess in the
Mhm.
1920s. But nowadays, no one's doing that nowadays because there's not any really new physics to see there. What
Sure.
people are doing nowadays are building surface detectors, very, very large surface detectors, several square kilometers.
Wow.
And with those very large area detectors are looking for the very, very high energy, the most
Mhm.
energetic cosmic rays coming in, because as I said, they are of great interest because we don't know where they're coming from. Now, the
Oh,
problem
okay.
is the higher the energy of the cosmic ray,
Mhm.
the less likely it is to occur. The spectrum falls very steeply. with energy. And so these really high energy cosmic rays come in at a rate of about 1 per square kilometer per year.
Wow. Okay.
So if you want to detect them, you have to have a very big detector,
Okay.
several square kilometers. And of course, you can't put that into space.
Right.
So
right.
you just put it on the ground. And I have some, I think a slide that shows that if you like.
Yeah, no, sure. I do have a question though. So then what's the reason why we couldn't do kind of a similar thing instead of looking at it in the context of a really, really high energy muon, that we couldn't look at potentially a really, really, really high energy pion? Is there something about the pion that makes it harder to discern in terms of the amount of energy that it has, or?
No. As I said earlier, a pion going through the scintillator will essentially behave just like a muon. It'll produce a certain amount of UV photons. But remember, when we detect these muons or when we detect the pions, we're not detecting the energy of the muon or the energy of the pion.
Okay.
The muon passes through the scintillator. So all we know is that a muon went through and it deposited some energy, but we don't know what the energy of the muon is. If you want to measure the energy of the muon, then you have to do something else.
Okay.
You have to couple your detectors measuring the track of the muon with a magnetic field.
Okay.
And the curvature in the magnetic field would tell you the energy of the muon.
Okay.
And people did that back in the 70s. They put magnets up in I don't know if it was a satellite or a balloon, to measure the energies. But this simple system of just having 2 or 3 scintillators, it won't tell you the energy of the muons. It will just tell you that they're there.
There or not. Okay, I see. Yeah. So if there's any other slides in particular.
Okay. Let's see. I don't remember what I have here. And sorry, I left a gap between each slide so I could write something.
Yeah, no, absolutely fine. No, I appreciate that.
It makes it hard to come through. Okay, yeah. So cosmic rays. Oh, I was wrong. It wasn't in the 1920s. It was in 1912.
Okay.
In 1912, this guy Victor Hess, he went up in a balloon and he went up to almost 18,000 feet. And of course, he didn't have oxygen, so he was a very, very, very brave individual. But okay, let's see. Yeah. So and okay, there's an interesting story with this. I think all your students know about electroscopes, right? If you rub a rod with a piece of cloth and then you touch the rod to a piece of metal, and then your electroscope there's a vacuum here inside the electroscope, and then there are 2 thin leaves. They'll become the charge that you put onto this electrode at the top will get deposited on the 2 leaves, and then they'll separate because like charges repel each other. Now, if you make a really good vacuum, then this will stay charged for quite a long time. If it's not a good vacuum, then just the air will pick up the charge. But if it's a good vacuum, it'll stay charged, but it won't stay charged forever. And so people can make really, really good vacuums back in the very earliest part of the 20th century, but they found that still the electroscope discharged.
Okay.
They finally figured out, and right at the same time, they learned about radioactivity. Radioactive decays of uranium and thorium and so forth. And so they figured out that, the reason this discharges must be because of the natural radioactivity that's in the walls and stuff. That radioactivity also is charged particles, and the charged particles hit these leaves and they knock the charge off. So over time, this natural radioactivity will discharge the electroscope.
Wow.
So then some people, and Victor Hess in particular, had the idea, well, this radioactivity is coming from the ground. There's uranium and thorium in the ground. If I get away from the Earth, then there's no natural radioactivity around, and then the electroscope should stay charged indefinitely. And so he took one of these. This is actually a model of one of the electroscopes that he took with him up in the balloon. And what he found is that here's the rate of ionization and the rate of charge loss of the electroscope. He found out that and this is the altitude in kilometers. When he got up to a few thousand kilometers, it was discharging more rapidly than it did on the surface of the Earth. And that was really peculiar. And then I don't know who it was concluded it. Maybe it was Van Hess or maybe somebody else. Well, there must be radioactivity there as well. It's not
Right.
coming from the Earth. It must be coming from outer space. And so that was the discovery of cosmic rays.
Wow, that's incredible. Wow, yeah, a true testing experiment with some outcomes that were unexpected. So what are some of these slides you're kind of going through here?
Yeah. Okay. Well, this is maybe too much detail, but this is the spectrum of cosmic rays. So on this axis is the energy, is the flux.
Hmm.
This is the flux, the rate at which cosmic rays are hitting the atmosphere.
Okay.
And the horizontal scale is the energy.
Of the actual particles
Yeah.
themselves.
But you see, it goes over many, many orders of magnitude. Here it goes from 10 to the 9 to 10 to the 21
First, yeah.
electron volts. And on the vertical scale, it goes from 10 to the 4 per square meter per steradian per GeV down to 10 to the minus 28. So a huge number of orders of magnitude.
Hmm.
But if you plot this on a log-log scale, it's pretty much linear.
Hmm.
So it means that the flux of the cosmic rays is falling like e to the minus some power, the energy to minus some power, and that power turns out to be essentially 2.7. So this falls like 1 over the energy of the cosmic ray to the 2.7 power.
Oh, okay. Interesting.
And so the very highest energy cosmic rays, the ones that are coming from outside of the galaxy, are these. These are the extragalactic cosmic rays. And so these are what people would like to study.
Right.
But because the flux is falling so much with energy, when you get out here, when you're down around these energies, then there's about 1 cosmic ray particle per square meter per second, quite common. But when you get up to these energies, then the rate is 1 particle per square kilometer per year.
Wow.
And so if you want to study those particles, this just shows the same thing. Let's skip over these. I think I have. Yeah, so if you want to study those particles, you have to build a detector like this. This is a detector in Utah. It's called the telescope array. It says proposed, but this is a very, very old slide. It's been running for many years now. And yeah, let's see, this is 5 kilometers. So, it's about 10 kilometers by 10 kilometers.
Wow.
And each one of these dots that you see is one of these. So, and it's basically what I just showed you. It's a scintillator. Inside of here is a scintillator detecting the muons as they go through, and then sending signals out. And then there's an antenna here for sending the signals back to some central base. This is a solar cell to keep the system powered. And so I don't know how many, you can count the dots. I think there are maybe 1,000 of these distributed over about 100 square kilometers out in the Utah desert.
Wow. And how many scintillators are at each black dot? Is it just one, or are there?
No, I think it's just one, but it's kind of big. It's the size of this, so it's bigger than the scintillators I've been showing you.
Yeah.
But yeah, it's just one scintillator in there.
Oh, okay.
I think here, well, maybe they have 2. I guess they have 2 scintillators, so they are doing a coincidence in here. You have 2, because otherwise you'd be swamped with noise. So there are 2 scintillators, one on top of the other, inside of this box.
Okay, gotcha.
So the problem is, if you want to do interesting cosmic ray physics, you've got to have a lot of money so that you can build something like this. It's not something, unfortunately, high school students can do.
Sure. So outside the realm then of probably cosmic rays in particular, for students now who are thinking about, okay, so what are some sensors that I could potentially build to collect data for? What is it potentially that you might be able to suggest might be interesting? Are there other types of particles besides muons, or in our case, we talked about pions as you increase in altitude, that students might be able to collect data for, to be able to maybe come to some conclusions about? Maybe something relating to new science, right?
Yeah. You mean if you put a detector up in space?
Right.
Yeah. Well.
And not necessarily stating what it is that we are detecting, right? But if you have any suggestions on, if we could detect this, that could potentially lead to interesting science?
Yeah. It's not an easy question because that kind of physics was done, like
Sure.
60, 70 years ago. So you want to find something that hasn't been done already.
Maybe not hasn't been done, but maybe in the context of how we maybe look at that data is new. So can you think of any other particles, I guess? And maybe not elementary particles either. They could be macroscopic particles as well.
Well, really, as I said before, essentially all the particles are pions, and then secondary particles that come from the pion decays. There certainly aren't a lot of any unknown particles being produced because they we already know about, which
right.
doesn't mean, well,
I was thinking more so along the lines of maybe, in space, there's a lot of hype around, with James Webb Space Telescope right now, right? And in terms of what it is that it can actually see in terms of detection. So, in their case, right, looking at gas spectroscopy, right? So I saw you had some slides about, solar weather in particular as well. I wonder, are there other quantities that students might be able to collect in the context of maybe not a elementary particle in terms of, quarks and things like that, but maybe in the context of maybe not helium or nitrogen nuclei or, whatever they might be looking for in the gas spectroscopy to be able to tell the age of maybe a dust cloud or something like that. But maybe if they could collect, a particle that is coming from a different galaxy in a different context, can you think of any maybe element that we might be able to detect as a physical particle?
Well, at the low energy side, the lowest energy cosmic rays, they're mostly coming from the sun. The sun produces a lot of very low energy cosmic rays. Sorry,
and why is that?
Well, there's this solar wind, right? And every once in a while there are continually eruptions on the sun.
Gotcha.
Solar flares. And when they occur, they send out streams of electrons, maybe some protons, but mostly electrons. And that's the solar wind. And so in this case, then these are low energy electrons, not protons, but maybe some protons, but mostly low energy electrons that hit the Earth coming from the sun.
Okay. Do those undergo the same process as high energy protons when they interact with our atmosphere, or no?
No. These are too low in energy.
Gotcha.
So, but they are electrons, so you could detect them as charged particles.
Okay.
And then you could then maybe look at the time rate of change of the flux of these particles, and that would tell you something about the time, what's going on as a function of time on the sun.
Okay, yeah, activity on the sun, right?
Yeah, right. Maybe you could correlate it with sunspots or something.
Okay. Is there any information maybe about, not necessarily planets, but any information about galaxies outside of our own potentially, or I shouldn't say that, solar systems outside of our own system, right? In particular, where we might be able to collect information about, so I gave the example of like a hydrogen or helium nuclei, right? In the context of, the sun, those are the first things I think of, based on my own understanding, because, we have fusion happening there. When we think about fusion potentially, right, what other particles is it besides hydrogen and helium that you could potentially detect if you could, right? Like, is there a presence of any type of nitrogen on the sun as well, or outside of the sun? When we think about where elements that exist on Earth came from, right? Is there anything that we could get as information about potentially, if we can detect this particle, then that gives us information potentially about where it came from, maybe, or what it is telling us by being able to detect that?
Okay, well, the sun is mostly hydrogen and helium, as you mentioned.
Mhm.
Eventually, as the sun evolves, it's going to start fusing higher. It's going to run out of hydrogen. It's going to start fusing higher, more massive nuclei, and then
Okay.
start producing carbon and
Oh,
nitrogen
wow.
and and but in order to see what elements are on the sun, you can't determine that by looking at this solar wind, this
Right.
solar. To do that, you would have to do spectroscopy
Mhm.
on the visible photons coming from the sun
Right.
to see if you'd see absorption peaks.
Okay.
Let's say if there's some iron, there is some iron in the sun. So if you wanted to measure how much iron is in the sun, you could look at the the visible light coming from the sun and measure the spectrum of that with diffraction grating or something, and then
Interesting.
you'd see that there are absorption peaks, where
Uh-huh.
the light in this particular frequency or wavelength is being absorbed by iron.
Right.
Measuring the amount of that, you can measure the amount of iron in the sun. But
Oh, wow.
that would be done by looking at the visible light from the sun.
Okay, I see. And that would be a spectroscopy way, like a gas spectroscopy variation.
Yeah, yeah,
Um,
yeah,
so
yeah.
I actually have a question. This might be kind of I might be going way outside the bounds of maybe what makes sense, but is it possible then, right? Like, so you said as the sun slowly starts to, I guess, quote unquote, die,
Yeah,
for lack of a better example,
yeah.
that helium that the hydrogen is fused into will then fuse into heavier and heavier elements potentially, right?
Huh?
So, if let's say our sun was massive enough and then it did undergo, a supernova,
Mhm.
if that was true, right, when it sheds a lot of,
Mhm.
that other material should then be technically heavier elements as well, shouldn't it?
Yeah,
So
yeah.
then is it possible that some of those elements then might be able to make their way from one solar system into another solar system inside the same galaxy, or even from one galaxy to another galaxy?
Uh, yes, yeah.
So are those particles then detectable, would you say, or no?
The heavier elements.
Yeah, potentially heavier elements. So like if
Yeah,
you were to be able to detect, I don't know, nitrogen or I'm going outside of my comfort zone here. What would be the heaviest, I guess, element that you could, I mean, can you fuse whatever into whatever? Is there a limit to how much you can fuse?
yeah. The limit is iron.
Okay, so
Up until iron,
uh,
you can. It's but by fusing nuclei together up till you get to iron, the resulting fused nucleus is lower in energy than the initial ones, and so it
I
releases
see.
energy.
Oh, okay.
But
All right,
above
so it's kind of
iron,
like a
it goes the other way around. You get energy not by fusing, but by fissioning.
right by okay
And,
by
and, and
splitting
iron
apart.
iron is the borderline.
Oh, I see. So
So
could you detect iron then potentially?
in the cosmic rays, yeah, and people have done that. It's not easy.
Okay.
Um, One way to do it is, if it's iron,
Uh-huh.
a proton just has a single charge.
Right.
Iron, I don't know what the charge of iron is, but it's more than one. It's like
Right.
20 or so. It's much more charged than a
Mhm.
proton, and so then it loses energy much more quickly.
I see.
So a proton will go deeper into the atmosphere before it loses its energy.
Uh-huh.
But a nucleus, because it's much more charged than a proton, will lose its energy, higher up in the atmosphere.
Right.
So if you could detect, the point at which
Uh-huh.
these cosmic rays are interacting in the atmosphere, not on a particle by particle basis, but on a statistical basis,
Right.
you can say whether there are heavy elements,
Oh, wow. Interesting.
heavy element component in these cosmic rays.
Okay. So I wonder then if we are in, something like orbital space, is that a high enough altitude potentially to maybe make those collections?
Mhm.
Like would it be theoretically possible? Not saying that yes, our students might be able to do that, but would that be something that could be
Mhm.
possible?
Mhm, mhm. Well, I'm talking very theoretically here,
Sure.
whether it's doable or not, but yeah, if you had different different composition of the primary cosmic rays, protons, and then say helium, maybe some carbon and some iron,
Right.
and each of these on average would start their shower at a different height in the atmosphere.
Right.
So if you could make a measurement and then see the distribution
Hmm.
of where the showers start, you might see a multi-component distribution, one for protons, one for carbon, another for
Oh,
iron, and so forth.
yeah.
But that would be an extremely hard measurement.
Right. Yeah. And we'd be talking probably a lot of satellites then too, right?
And as I said, you can't do that on a particle by particle basis. You just have
Right.
to on a statistical basis. Look at a lot of interactions and see
Right.
that there's one distribution that interacts roughly at this point in the atmosphere, and another distribution that interacts at another point in the atmosphere. But both of these distributions will be very broad. They'll
Right.
overlap. So
Yeah.
you can't say on a cosmic ray by cosmic ray basis. But
Sure.
it's just
Okay. Interesting. So, I mean, I think that's a good amount of stuff for some of our students to kind of go off of when they think about, what is it that if they were to develop their own sensors, right? And they think about detection, what is it that they can detect? So I think you gave us a great example in the context of these cosmic rays, right?
Mhm.
Detecting singular muons, right? And being able to use a scintillator and a photomultiplier in that way. And, its similarities and very clear differences from how a light sensor works that they've been working with, measuring just a whole, flood of photons rather than a singular photon. If students want to learn more, if they want to get involved somehow, obviously we're a global campaign. So, say a student is in Asia or a student is in South Africa, where could they go? Are there any resources, things like that you can kind of point us to?
Mhm. Well, if they wanted to build their own detectors
Mm-hmm.
like these,
Sure.
they can go to the QuarkNet website,
Okay.
and there's a user manual for this cosmic ray detection kit,
Great.
and they could look at that and maybe consider building their own, getting their own scintillator, and
Yeah.
then buy photomultiplier tubes. It's the photomultiplier tubes are roughly $1,000 a piece,
Oof.
so
Okay.
so it's cheap, but that could possibly be done, and maybe Fermilab could assist with that.
Okay.
If they're in the U.S., they can, their school can become a member of this QuarkNet collaboration, and then their teacher can get one of these kits from Fermilab.
Oh, okay.
There are about 10 teachers throughout New Jersey that have these detection kits.
Mm-hmm.
But,
Okay. That's awesome.
if they're not in the U.S., I'm not sure how they could get them other than making them
Making them
themselves.
themselves. Okay, but that information is available. So if I reach out to you for
Yeah,
some
I
of
can
those
send you the
links,
link.
yeah, okay, awesome. So then those are links that I'll definitely post for us then as well. So I don't want to take up too much more of your time. I know we went way over our time here as well. Sorry for all the questions. I just wanted to make sure I tried to create as cohesive as a process so the students could follow along as well. But thank you so much for your time, really, Professor Schnetzer. I certainly appreciate it, and I know that the students appreciate it too. Thank you so much.
Yeah, it's been
All
fun. I enjoy doing this, and yeah, if any of your students have questions, as long as I don't get too many emails, if someone want to email me a question, I'll try to answer it.
Yeah, definitely. We have our own kind of community boards. I could compile some of those questions and send them
Okay.
over to you to be able to answer too. All right. Is there any last minute stuff that you want to kind of include here? If not, we'll go ahead and conclude.
Well, it depends on what you want to do. If you want to conclude now, it's 5 o'clock. It's fine. But I could say one thing that is a very interesting thing that you can do with these detector kits that the students that we have in the summer do, and that's to measure the lifetime of the muon.
Oh, okay.
You want me to say a little bit about that?
Yes, please.
5 minutes. Okay. So here are three of these plastic scintillators that I showed you. And so we stack up three of them. And now, once in a while, it's very rare, a muon that comes in might stop. It lose all of its energy and stop in that scintillator.
Oh, wow.
It doesn't happen very often, and roughly once in every 10,000 muons that come in will stop. But then if it stops, it loses all its energy. It's just sitting here.
Mm-hmm.
And then with an average lifetime of about 2 millionths of a second, it will decay. Mm-hmm. And when it decays, as I showed on a previous slide, it'll decay to 2 neutrinos. We can't detect those. Those just go flying off. But there's also an electron. And this electron will produce a signal here. It'll also produce a signal in that detector.
Okay.
So so what you do is you make a logic. So you measure a signal from A, B, and C. And now you look for an event where you get a signal from A and a signal from B, which means a muon came in, and then you veto it. If there's a signal from C, then you veto it. But if there's no signal from C and there was a signal from A and B, then that indicates that maybe the muon stopped in B.
Oh, okay.
It doesn't guarantee it, because maybe a muon came in like that.
Right, yeah.
But it's some indication that you have a stopped muon if you have A and B and not C.
Okay.
So then you wait for about several microseconds to see if there's a delayed signal that comes from this electron that appears when the muon decays.
Okay.
And then you can plot the time of that delayed signal. And here's a plot. And if you do that, you actually get essentially a perfect, modulo the statistics, a perfect exponential.
Wow.
The number of signals that you see as a function of time goes like some constant times e to the minus t over tau, where tau is the average lifetime of the muon, which is 2.2 microseconds. So here, this is some actual data that students took, and there are error bars on the data, red points, and then you fit this with an exponential, and you can measure this value of 2.2 microseconds to a percent or better. It's a very, very impressive measurement.
That's crazy.
Now, this is also very interesting in terms of physics, because this is getting into real, one of the main things of quantum mechanics, which of course is the basic theory of physics. And this shows one of the weird things about quantum mechanics. There are many weird things about quantum mechanics, but here, every muon that stops is identical. There's no difference from one muon to another. But nevertheless, some muons decay, at this time, some decay at this time, some here, some here. That they decay at different times, even though all the muons are identical. So this is just an important property of nature that comes from quantum mechanics. Even though the muons are all identical, to say when a particular muon is going to decay, we can only give a probability.
I see.
There's a certain probability that a muon will decay after 1 microsecond. There's another probability that it will decay after 2 or 3. It goes down as a function of time. But we can't say with certainty exactly when a particular muon is going to decay. And so this exponential distribution you see comes directly from the quantum mechanics. The fact that the probability, if you have a muon sitting here, the probability that it will decay in the next instant of time is independent of the past history of the muon. It doesn't matter how long. It doesn't matter how long the muon has lived. From a given time, the probability that it'll decay in the next instant is a fixed amount, whether the muon has already lived for 10 microseconds or was just created. And that's what leads to this exponential curve.
I see.
And that's a property of quantum mechanics. So just by doing, it's a fairly simple measurement to do if you have this kit, and you measure this time, this small time, very precisely. And the fact that it fits an exponential is showing you something very deep about quantum mechanics.
Yeah, right. With the distribution, with the probability distribution in particular. That's amazing.
There's really interesting things you can do with these rather simple detection kits.
Yeah. So I think that gives a lot for our students to think about as well when they think about, if I do go on to develop my own sensor to collect data, not just what the raw data is showing us, but what are the different measurements that we can make that might tell us potentially inferences about other things as well. I think this is a great example of that as well. I'm really glad you took the time to tell us about this. Thank you.
Okay.
All right. So like I said, I don't want to take up too much more of your time. Thank you so much, Professor Schnetzer, for taking the
Okay.
time to share some of your insights with our students, things like that. If you guys have, as students now, any questions that you would like to reach out to Professor Schnetzer with, feel free to email me directly at dlee or daniel.lee@maxiq, and then I'll be able to push those things over to Professor Schnetzer, or post those comments in Canvas, and we'll make a conglomeration of them and be able to ask Professor Schnetzer as well. Thank you again so much. I really appreciate it. All right.
Okay. Thank you very much.
Thanks.